Hello everyone. So, today we'll be working on some questions relating to circular motion and gravity. And since these questions were taken directly from the class notebook, it will probably appear on the test tomorrow as well. Yeah, so let's begin. So, first question. You're driving a 700 kg car at a speed of 25 meters per second around a corner with a radius of 30 meters. So, first of all, determine the weight of the car. Okay, this question, we can just use the formula of weight equals to mass times gravity, and just plug in the numbers, times 9.81, sorry, yep. So that will give us 6,867 newtons. Yep. So, for the second question, which is asking for the centripetal acceleration of the car, I'm going to do a similar thing. Just use the equation from the data booklet, which is the centripetal acceleration equals to v squared divided by r, and plug in the numbers, which is 25 squared divided by 30. And that will give us 20.8 meters per second square. Yep. So third question. Determine the minimum coefficient of the static friction to keep the car from slipping. Okay. So, in a corner where there is a car trying to turn around, if you want to keep the car from slipping, you have to keep the car in a circular motion around the track, which means that there has to be a centripetal force that is like pulling it inwards. Yeah, so let's see what are the centripetal forces. For the car, the only force that matters horizontally are just the friction force. So, friction force. Since it's the only force that matters, it will also be our force net, which in a circular motion will be the force of circular motion. Yeah, so since we know this, we can just equate the force net, which is the centripetal force, to the force of friction. Yep. Now we can just substitute these with different equations and to figure out the actual answer. So what can we do is that we can change force centripetal force into mass times acceleration, since this is the force net. So we can just use the mass of the car times 20.8. This will be the force net, which is also the centripetal force. And for the right side, we'll use the friction force, which is mu, the static friction coefficient, times the mass times 9.81. So as you can see, the numbers some numbers kind of cancels out. 700 cancels out, and then we'll just get mu equals to 20.8 divided by 9.81. So the static friction coefficient of this question will be 2.12. Well, supposedly the number is supposed to be decimal number. However, apparently the teacher made this questions in front of everyone, so he didn't really like look at numbers. But yeah, it's fine. This is the right answer, I'm pretty sure. Yeah. So question 4. If we hit some ice, which means the friction is gone, to describe the path of the car. Yep. Again, let's draw it out. So what's happening? So let's say it's undergoing a circular motion. However, there are some ice here which cause a loss in friction. And since friction is basically our only force, which is also our centripetal force, the centripetal force will be gone. So what does it mean when the centripetal force is gone? It means that the object is no longer undergoing a circular motion. So, let me draw a normal circumstance. So normally, with centripetal force, the car would just go in circle, obviously. But since there are ice here, when it meets the ice, there will be no more force to pulling it inwards, so it will just continue sliding over here and sliding away because of the inertia of the car. Yeah, So that's the first question about circular motion. And now let's go to the second question. So a bungee jumper, mass of 60 kg, jumps from a height of 50 meters connected to a 20 meters long bungee cord. And what are the forms of energy of the jumper at each point? So calculate the value for each at different positions. Yeah, so before this question, just consider what kind of energy are there. So obviously there are PE, potential energy, gravitational potential energy, caused by the gravity. Yep, and obviously KE, because the jumper is moving, it's like jumping down. And there also be the EE, which is elastical energy from the cord. Yeah, so we can just consider what would these values be at different positions for these sub questions. So first one's the top. So what happens at the top? So at the top, it hasn't stopped falling yet, so KE will be 0. What about EE? So for EE, since the cord is not stretched at all, it won't really produce any electrical energy to pull someone down or up. So again, it's 0. So the only force remaining will also be the PE, which is potential energy, and it's just mgh. So we can just multiply the value 60 times 10.81 times 50. 60 times 10.81 times 50, which is 2.94 to the power of, actually, let me just use an actual number. It will be 29,430. Okay, so this also tells us a very important information, that was total energy. Since we're assuming a closed system, again, the energy in different positions, the total energy of the energy in different positions will be the same. And we can see the total energy will just be 29,430 throughout all the places. Yeah, so this will be useful later as well. Yeah, so what about the second part? After falling 20 meters. Okay, again, consider the forms of energy. PE, obviously there will be PE, and we can calculate that with mgh. KE, we don't know, and we can't really calculate it with 1 over 2 mv square, but we'll sort that out later. And EE, which won't be any value, because will be 0 actually. Will be 0 because if it's at 20 meters, it's at an equilibrium position, which means there's no stretching. Yeah, so first of all, we can calculate the PE. PE will be again equals to mgh, which is 30, 60, which is 17,658. Yeah, joules. And EE will be obviously be 0 because it's at the equilibrium position. And at last, KE, we cannot calculate it by velocity. I mean, we technically can, but that would be annoying. But what we can do is that we can have the total energy. Since it's conserved, we just minus the total energy with the potential energy of 17,658. So this will be the remaining energy, which will be our KE. And that will be 111,772 joules. Okay, third part of the question. At the bottom. So what happens at the bottom? Let's consider PE first again. If it is at the bottom, it will be 0, because H is 0, so mgh will equal 0. So PE will equals 0, obviously, and KE, what will the KE? Okay, so imagine a jumper falling down, and when it reaches the end, it will get pulled completely by the cord, and at some point, like, not at some point, but at the very bottom, the KE, the velocity of the jumper will be absolute 0, because it's transitioning from a falling motion to a going up motion. So at the complete bottom point, the KE will be 0, because the velocity is also 0. The KE is 0. So the remaining one is just the EE, which is our total energy. 29,430 joules. Yep. So yeah. So second question, what is the K, which is the spring constant of the cord, if if they bounce safely? Okay, so this is a bit of a simple harmonic motion question, but it's fine. So most importantly, we can use the value we have gotten from the last part, which is that EE at the bottom is 29,430. So we know that EE is 29,430. And at this point, you can just use the equation that relates the spring constant to the elastical energy. That will be EE equals 1 over 2 kx squared. Okay, simple equation again. So there are two values that we know, EE, which is here, and x. So x here is a displacement, which is also how much the cord have stretched. So from the question, we know that the cord is 20 meters long. So it would be like that normally, 20 meters. However, at the bottom, it will be stretched to 50 meters. So it has stretched for 30 meters. That's the difference. Yep. And we are just plotting the numbers that we have just figured out. Okay, 30 squared. So manipulation 2 times 9. Oh, sorry. 2 times 29430 divided by 30 to the power of 2, 900. Press my calculator and that will be 65.4. That will be our K. Remember the units, which is Newton per meters. Yep. And third question, what is the acceleration at the bottom? So here we will use another equation that we know, which is F equals to negative kx. So how is this related to the question? Well, since we know the mass of the object and we know we want to find acceleration, just substitute force by mass times acceleration, and we just plug in the numbers that we know again. So k will be 65.4, and x will be 30, and mass will be, I'll just put the mass to divide here, so mass will be 60, yeah, 60, and this should be our acceleration, and the answer will be 32.7. Actually there's a negative, so negative 22.7, which means it's going up at the bottom. That makes sense, right? Like at the bottom it's pulling it up. Yeah, so that's for the third question. Okay, for the fourth question, so what's the motion if there are no energy loss, or there are energy loss? So let's first consider what will happen if there are no energy loss. So if energy is conserved in the system, you can imagine what happens is that the first will go down and it will go up, right? And because of the conservation of the energy, the place that go up will be the same as beginning point, like they will be like the same height. So what does it mean is that this motion will continue forever until I don't know, because the energy is conserved. So go forever, just go up and down. Okay, by the way, I draw it sideways, but it should be just like that, okay? But you get my point. If energy is conserved, the person will keep going up and down until never. It never ends, okay? Okay, however, what about the real life case, which is when energy is not conserved? This means that energy may be lost to thermal energy or friction or air resistance maybe. So what will happen is that this will become a simple harmonic motion. This is the first try. It's going right down, and when it goes up, it won't reach the beginning height. That is because some of the energy are lost to thermal energy or frictional energy or other energy. Because of this, it will keep slowing down and be damping, and at the end they will reach a equilibrium point at the middle. Yeah, so the answer will be, if there are energy loss, the motion will stop after a while because of the loss of energy. Okay, that's a pretty bad answer, but you get my point of that the energy is like lost, and the height and the different, yeah, it will not reach a high and not reach a low. Yeah, that's 5 points. And six, last and five actually, last question: where did it end up after energy is lost? So the approach to this question can be using a simple harmonic motion thing. Yeah. So we know that F elastic equals force of gravity. And we know the elastic force is the, so okay, let me explain this actually. So why would we know that force of elastic is force of gravity? That is because, let's say the cord is, let's say there's a person here damping again and it stops at this point. So the forces acting on the person will be two forces. One is the elastic energy pulling it up, one is the gravity energy pulling it down. And if two are the same, if these two are the same, the net force will be zero, which means that it will stop at that point because there's no acceleration, there's no more movement or change in speed. So we know that F elastic equals the force of gravity. Yeah, so now just plug in the numbers really simply. We know that force of elastic equals negative kx, and Fg will equal to mg. Just plug in the numbers so we know. Mass is 60, gravity is 9.81, and the k will be gravitation. I mean the spring constant will be 65.4. So we will know that. Okay, negative 9.81 because it's going down, and the displacement we're talking about will be going down to. So the negative x will be what? Oh yeah, will be 9 meters. Will be negative 9 meters because there's a negative sign in 9.81. Yeah, cancel out the negative. So we know that the equilibrium, the equilibrium point of the mass will be 9 meters down of the, yeah, will be 9 meters down. So that, so we can just add this by the initial, like a starting position of the cord, which is 20. So we know that the stopping point will be 20 plus 9, which is 29 meters. So the last question is about graphing, and we have to graph EG, EK, and E total graphs for a projectile flown up. So the question is, what will the graph, which is energy vs radius, look like if the projectile has enough speed to escape the Earth's gravitational pull and go into deep space? So let's draw the axis first. This will be R, which is radius, and this will be energy. Yep. The easiest part of this question will be the EG part. Oh, what did I just? Okay, that's because we know the quantum equations of the EG. That will just be GMM divided by R, negative GMM divided by R, negative. Remember, yeah. So since R is being divided, that means that the higher the R is, the smaller the energy will be. So the graph will look something like this, approaching zero when R gets too large. Okay. So what about KE? EK, EK. The EK when the projectile has enough speed to escape the Earth's gravitational pull. So from the equation booklet, we know that the velocity escaping, the velocity needed to escape, will be square root 2gm r. And then in order to get the KE, kinetic energy, we just put 1 over 2m squared on that, which which is, I mean 1/2, 1/2, and with that one being squared. So the square will cancel out with the square root, and you get something like GMM divided by R. So you can see that this is actually the exact opposite of this one. One is being negative, one is being positive. Therefore, the KE will just be like this. This will be KE, EK, which is labeled as EK, so it will be labeled as EG. So, what about total energy? So total energy will be adding the two energies up. And since they are the same magnitude, but the different, like one is positive, one is negative, the total energy will be in the middle in here. Okay, second question. This is actually two. There's three. What if it has less than escape energy? Less than escape energy. So again, we draw the same graph, and the EG will be the same because it's always an equation. I want to draw it better, so I'll be something like this, like this. Yeah. So if it has less than escape the energy, so it means that it's basically GMM, the K of GMM there by R, but it's a smaller value. So let's multiply by 0.8, let's say. So in a mathematical perspective, this is basically vertically transforming the function by 0.8. So it will kind of be like getting compressed compared to the first one right here. So it will be, let's say, it will be something like this. Because obviously here being compressed as this starts here and this starts here. It starts in the middle and this starts in the top. Yeah. So that will be the two energies, and what about the total energy of these? So total energy will be a line from here to here. That's because the KE will forever be lower than the EG. Therefore, there will be a line here, which is the total energy. Yeah. Okay. Last question. Inside of a projectile, what about objects put into various orbits? Various orbits. Okay. Let's draw the graph again. So again, we'll draw the potential energy because it's always the same. Okay, what about orbiting energy in different orbits in the radius of R? So from the data booklet, we know that V, orbiting velocity, that the velocity needed for an object to orbit in a certain radius something, is square root GM divided by R. So we take the same method. We can just use 1/2m and square that number on that one to get the kinetic energy, and it will simplify to something like GMM divided by R 2R. Yeah. So if we compare this into negative GMM divided by R, we can see it's pretty similar. However, this one, it will multiply the R by 2. That means that R will have a greater impact on the total value as R goes bigger. The kinetic energy will go even smaller. So we can see it something like this. We factor out 1/2. It will be 1/2 GMM divided by R. So again in the mathematical perspective, this is basically a vertical transform, compressing it by half. So this will be half of the another function at the bottom. So EG and this will be EK. And EG will equal to negative GMM R, and EK will be GMM divided by 2R. Yep. So this is half of this, by the way, and let's get a total energy by adding them up. So GMM, negative GMM divided by R plus GMM divided by 2R. We can calculate this by multiplying the denominator of the first one by 2. Just do this, and if you add them up, you'll get the total energy will be negative GMM divided by 2R. So this is basically, again, the opposite version of this one. So we can just draw symmetrical but negative thing here. This will be the E total. Yep, so these are the energy graphs, and I wouldn't say they're complicated, but it requires a bit of thinking, I guess. Yeah, just remember that the kinetic energy can always be found on a data booklet by the escape velocity or the orbiting velocity, and I think 1/2 sort of behind or on top of that. Yeah, so that's it for the physics.